Okay, a little bit about friction for Physics 11 students. So we're going to start a lab. You have a worksheet on friction. So I'm going to give a little bit of background information examples. Turns out friction is, oh, I forgot the focus lock here. Hold on a second. It's never good. All right. Turns out friction does depend on the material. It depends on the weight. Focus locked in it. Stick. It depends on the weight of the object in contact with the surface. It actually ends up being the normal force, the contact force, because we'll see that you can make something more stick to the ground better if you push down on it. You don't change its mass, you don't change its weight, but you make more normal force because you push down more on the ground. So in the lab, we'll go ahead and we'll actually, as a kind of a follow-up, we'll make a graph of the force of friction required to pull something. All right, so if you have something and it has some mass, right, and we pull it, if we pull it at a constant velocity, the force of friction acting on the bottom must balance out with the applied force. So if I make a really free body diagram, it's easier to see. This is the applied force. I'll call that force of a pull or something. And then the frictional force resists that. Now the other two forces we have are the normal force and the gravitational force, Fg. All right, and in most cases, the normal force and gravitational force are simply equal to each other, equal and opposite. So if this is is a 1 kilogram object and the weight is about 10 newtons, the normal force would also be about 10 newtons. Now the weight, technically, the force of gravity is negative 10, and the normal force would be positive 10. The heavier I make it, right, the more normal force it takes to hold it up. The more normal force there is, the stronger the friction is, it turns out. So actually, we determine the amount of frictional force that acts on something by pulling it, right, and seeing how much force it takes to break it free, and then also how much force it takes to keep it moving. So if we make a graph of the amount of friction versus the normal force, right, so as you increase the gravity, you increase the normal force, turns out this ends up being a linear line. As the normal force, which is essentially the weight of the object, goes up, the force of friction goes up. And if you do y equals mx plus b here, you get force of friction equals slope times Fn. And the slope ends up dimensionless. It ends up like a decimal, like 0.4 or something. 0.3, 0.8, 0.1. It ends up dimensionless because you can see it ends up being force of friction equals a number times the normal force. This can't have a unit because, well, the units on this is newtons, right? The units on this is also newtons. The slope of the line has no units. So it really is kind of like a scaling factor. And you'll see on the worksheet, we have a list of something called coefficients of friction. All right, so it turns out the slope of this line of frictional force versus normal force, the slope here ends up being something we call coefficient of friction. Coefficient of friction. And it has a funny symbol. It's a mu. Mu is the name. It's a Greek letter, mu. All right. And these are determined for every type of surface. So the equation for the force of friction ends up being simply the force of friction acting on something equals the coefficient of friction times whatever the normal force acting on the object is. Turns out surface area that's in contact does not actually come into play. And there's a good reason for that. It has to do with pressure, right? Turns out when you distribute the weight over a larger surface, there's less pressure at the surface. So even though there's more surface area in contact with each other, because the weight is distributed across that surface, there's less pressure. Therefore, it's kind of less frictional force. So it kind of washes out. The increased surface area you'd think would cause more friction, but actually because the weight is distributed across it, it doesn't cause more friction. Now that's not to say that there isn't something there, right? Race cars have really wide tires, right? So why would that be if friction didn't matter? Well, it does matter. So it's really not that simple. But anyhow, for our purposes, surface area doesn't matter, which is a little counterintuitive, but it really has to do with the pressure. If you can get like left to, it can still matter which way it's sliding. That's kind of the trick. The wider tires help it from moving left to right, which is a kind of a different ball game. But anyway, this ends up being the equation for the force of friction. And then what we saw in the lab was, well, there's actually two forces of friction that go on, because when we pull this thing, right, what ends up happening, if you look at the force of friction versus time, when you pull this thing, the force increases. And then at some point, once it breaks free, the force decreases and kind of levels off. So that point at which it breaks free is called the force of static friction. All right, max. It's the maximum value. It's the amount of force that it requires to break this object free. This force is called force of kinetic friction. Now, as a rule, it usually takes more force to get something moving than it does to keep it moving. All right? So the amount of force it takes to break this thing free and get it sliding, it always is a little bit more than the amount it takes to keep it sliding. All right? So we actually see in a table for coefficients of friction, we actually see two different. We see mu k and mu s. Kinetic coefficient and the sliding coefficient. Most of the time, the static coefficient is bigger than the kinetic. There's some on the table that doesn't show, I think, the static, or it doesn't show the kinetic, and that means they're approximately the same. Some slippery materials, they pretty much just start sliding. You don't really have to start this. Now, we'll come back and talk a lot more about this equation, how we calculate it, what we do with this. But the way I like to think about it is the friction, this coefficient, let's say it's 0.4. Let's say the coefficient is 0.4. Let's just look at a really quick numeric example. Let's say we have an object whose mass is 1 kilogram, and the coefficient of static friction is 0.6. All right? And I'm going to ask you, okay, how much force of friction do we have to overcome? So you're trying to figure out the force of static friction, the maximum amount, right? All right. So and that will tell us how much force we have to apply to this object to get it moving. So that force of friction, static, is going to be equal to the static coefficient times whatever the normal force is. Well, in this situation, and in most situations, Fn equals Fg. So Fg in this case must be mg, which is about negative 10 newtons. Therefore, the normal force must be positive 10 newtons, right? It must be, the equal and opposite. So when I plug the stuff in here, I get 0.6 times 10 newtons, right? Well, the coefficient, it's really kind of like a percentage, right? It's 60% of the normal force. You have to apply 60% of the normal force to break this thing free. All right, 0.6, that's how you find the percentage of something, right? You take the percentage, you convert it to a decimal, and you multiply it. So 60% of 10 newtons is 6 newtons, force of friction static. So it's going to take 6 newtons of force to break this thing free. And it's going to take something less than that to keep it sliding. All right? So I think of that coefficient as a percentage of the normal force. All right. Usually in this case, okay, so let's say the kinetic friction, mu sub k, let's say, is 0.4. Well, then if I want to figure out the force required to keep sliding it, it would be 40% of the normal force, or about 4 newtons. All right, so that's how you use this equation. Now, one of the things we're going to talk about in class as a follow-up here is where does friction come from? Why do different materials have different things? And part of it's the literal physical texture, right? But you can have really smooth objects that have an incredible amount of friction. If you take 2 pieces of glass and put them on each other and try to rub them, they stick like crazy. They're very hard to move. I mean, it's like an incredible amount of friction. The whiteboard, sometimes, if you stick them to each other face down, sometimes they're kind of hard to move against each other. Like 2 very, very, very smooth surfaces, if you touch them together, they're actually really hard to move. You see this in a variety of things, but I always think of like glass slides, and maybe you used in bio or chem, right? They're really stuck together. It's not because it's glue. It's because they're smooth surfaces, and they actually bond to each other. So friction is a molecular interaction on a lot of levels, right? The 2 surfaces, they're made of molecules, right? And those molecules have positive and negative charges in them, right? So depending on how the positive and negative charges are arranged in these molecules that are bonding, they may attract the other material it's up against, right? That it's up against, and that causes it to stick. So when you're breaking it free, you are actually breaking some chemical bonds. Could be some sort of van der Waals force, right? Could be like a little, just, an intramolecular bond, just, whatever that might be. So when you break it free, you are actually overcoming those bonds. Now, obviously, that's like looking at a microscopic level. If we look more macroscopic, also the texture might matter too. And in fact, the sandpaper can be surprisingly slippery on certain surfaces, even though it's the sandpaper side of the cubes we use. Even though it's sandpaper, you think about that being rough. Yeah, if you try to pull that across wood, it's going to be rough. It's going to stick. It's going to dig in physically. It's going to grab it like claws and dig in. However, if you take that same sandpaper and put it against something really, really hard, it actually slides pretty easily, right? Take a piece of sandpaper on a piece of metal and try rubbing it. It actually slides pretty easy. So it all depends, on the 2 materials, their softness, hardness, and then also whether or not they're chemically bonding to each other. And when you think chemical bond, you always think like it has to be a liquid or something, and it doesn't have to be. Solid materials can chemically bond to each other, right? It depends on their electronegativity difference. It depends on a lot of things. Like static electricity is basically chemical bonding, when you stick a piece of tape to the wall, it's chemical bonding. Now that's, that is sticky. That's got a little wetness to it, so that's a little different. But if you charge a plate up on your hair, you charge something with your hair. I say plate, which you guys will see in the future. In class, we use styrofoam plates a lot. You charge a balloon up on your hair and you stick it to the wall. Well, that is chemical bonding. It's polarization, and it's a van der Waals attraction of positive and negative charged particles. It's pretty cool. So anyway, it's a little tangent thing about where friction comes from, and why it always takes a little more to break it free, typically. Now, Teflon is very slippery. You know why? Because nothing bonds to it. I think it's the carbon and fluorine. It's bonded together so strongly that it doesn't bond to other things. To put Teflon on a nonstick cooking pan, it's like a crazy process. They have to like sandblast it, put a primer on it, coat it with the Teflon, bake it at just the right temperature to harden it, and then you can cook with Teflon. But if you get it too hot, it's not good. You can actually burn it. You can scrape it off. You gotta be careful how you clean it and all that kind of stuff. So Teflon is an amazing surface because nothing bonds to it. So it has very little friction. It's good for a lot of things because of that. But anyway, all right, tangent on friction, just kind of an overall talk about it, just a basic introduction. We'll get a little bit more concrete in the examples and problems as we move forward. But that's just a little something for now.